Today I'd like to talk about why we must stop building glass buildings. Glass box buildings are to climate action what fur coats are to animal protection. Some may see it as a lifestyle choice, but for others concerned about the climate crisis, a ban sounds about right. Glass buildings represent the modern world with their abundant daylight and views, but the fact is that the smartest glass can't hold a candle to a well-insulated wall. Imagine a person standing practically naked in the middle of Times Square in New York. Let's say it's winter, it's blustery cold winds, and this person is wrapped in nothing but a sheet of plastic and drinking piping hot cups of coffee to stay warm. What would you think about this person? We can imagine the path of heat flow as a diameter of a pipe. If my insulated wall is a straw, then my best window is a hose pipe. And my typical window is more like a drain pipe when it comes to heat flow.
Do people know about this?
So I find that a lot of people don't intuitively make that connection because unfortunately heat transfer is invisible. So imagine if we could see all that heat flowing out of our windows. Now imagine if what we saw flowing out of our windows instead of heat was our dollar bills flying out of our windows straight to a utility company who were then burning them up and producing carbon. That's essentially what we are doing with our buildings. If you imagine like a water drip, if you have even a single drop of water dripping from the tap, we call a plumber. But because we don't see heat going out of our windows, we just don't do anything about it. So people like me who work with building physics and energy modeling, we can see this heat loss in 2 dimensions and 3 dimensions, and we can make it visible for our clients using modeling. So I have this vivid memory from when I worked with a commercial sustainability consulting group. So we used to provide whole building energy modeling and LEED certification. And in 2002, I was working on the envelope of the Solaire in Battery Park City, which was, it's known as the first green high-rise multifamily building in the United States or anywhere. And it has pretty large windows for a residential property. So the manager who was leading the LEED certification at the time, John Amatruda, he came and asked me, he said, Smita, can't you do something about these walls to reduce heat transfer because we are getting dinged on our energy points? And I showed him the math. It's like, even if you keep fattening up the walls, the heat was flowing straight out of the windows. When you have 40% wall and 60% windows, and this becomes even worse in commercial buildings, your heat flows right out through the windows. It takes the path of least resistance. Another vivid memory I have is talking to the architect of record for the Bank of America. He was designing a dot pattern for the glass to provide shade. It's called frit. And he called me up and he was really worried. He was really concerned about the performance of the wall. And he was asking me, should I put 34% frit or 36% frit? And I had to tell him, just go with what looks best because it doesn't matter. It doesn't matter at all from an energy point of view, because once you've made that decision to put glass all over, that ship has sailed.
From a design standpoint, what are some other things that people can be doing to reduce energy use?
We have a lot of technology options these days, and we can save energy in many different ways. But the problem is that the choice to invest in a poor performing thermal envelope has an outsized impact on building performance. So if I install lighting controls, it changes my lighting energy use, right? So assuming they're all LEDs, maybe their lighting controls will have a negligible impact on heating and cooling. So you contrast that with the thermal performance of the envelope, which has a cascading effect on the building performance. So when you think about the energy that a building uses, it's coming from the building loads. The building loads impact the size of the building systems, and the building systems are what use energy to keep a building hot or cold. Now, when you have a poor performing envelope, it changes how large your air conditioning system is going to be. And that changes how much energy you're going to use, and as a result, how much emissions you're going to produce. It also changes how much refrigerant we use to charge those systems. So as many people know, the typical refrigerants used today, like R410A, have been improved to avoid affecting the ozone layer, which was a different problem. But when it comes to climate change, they are more than 1,000 times worse than 1 ton of carbon dioxide for global warming. So if you compare a ton of refrigerant to a ton of carbon dioxide, refrigerants are more than 1,000 times worse. And a lot of refrigerant actually ends up in the air because, it leaks out of systems when you're doing maintenance. And even at the end of life, sometimes it's not managed very well, which is why you have lead points for refrigerant management. So these early stage design decisions and simulations that model the loads before sizing the mechanical systems are key to optimizing the amount of glass in a building and the ultimate performance of the building.
So from a regulatory or policy perspective to kind of address this issue, do you see a need for like a ban or a limit on a percentage of glass in certain buildings, or maybe an aggressive standard for total energy use, and then let the modelers figure it out how to meet it? Or kind of what's kind of the solution set as you see it?
One thing that we have seen is that ASHRAE 90.1, that is the standard that people use to model their buildings. It has what is called the Appendix G, which gives you a guideline for modeling a baseline standard building compared to what you're building as designed. And that ASHRAE 90.1 standard, Appendix G, says that the baseline building cannot have more than 40% glass. That is a very effective way of showing the impact of your building when you have more than 40% glass. Where the problem is that a lot of people, when they are modeling these buildings, they model everything together. They model the envelope, the systems, the controls, and then after they've put in all their smart systems, when they try to tweak the window wall ratio, they don't see the impact so much because the impact gets hidden with all of the other measures that they are evaluating. So the right way to look at this impact is to model the loads just from the envelope first, and then model the rest of the internal loads, and let the energy model auto size the system. When you do it this way, you're really going to see the impact of the window wall ratio. So this is a very, geeky sort of detail, but I would say that a really effective policy would be to require that you have to model your loads of the dump building before you are allowed to put in all your smart systems, and even before you are allowed to put in your HVAC to size the system. So that would be a really effective way to, first of all, show the people who are designing the buildings the impact on the whole building performance. In a bigger picture where a lot of buildings are built without any energy modeling involved at all. It's only buildings that are going in for high performance that perform energy modeling. It can be expensive. So for the mass market, for most of the buildings that may be built without energy modeling, one in between step could be to start requiring energy modeling. And if that seems too onerous for the commercial market, then I would say yes, just having limits set on the amount of glass that's allowed as a policy might be the easiest way to have an impact. It's almost criminal not to do that where we are today with climate change.
Absolutely. Well, I feel like I've learned a lot this morning. Is that something that your firm, Energy Shrink, helps people with?
Absolutely. We perform energy modeling. We use what we call a pare down paradigm or a pare down framework, where we start with the envelope. We help people optimize the envelope as much as possible using passive design principles. If your electricity goes out, you want a building that is optimized as passively as possible without the use of electricity or any smart systems, so that you can coast through without having to rely on the systems. Your thermal envelope is your first line of defense. So you optimize your envelope, then you optimize your loads for your systems, how many square feet can be covered per ton of air conditioning, and then using that system sizing, the mechanical engineering partners would then downsize their mechanical systems. And then that would downsize your control systems. And all of this will result in downsizing your renewable energy systems. And this is the really interesting thing that people don't realize. When you downsize your loads, you downsize your systems, you downsize your renewable energy systems, you save so much money on your renewable energy systems that you can take that money and put it into your envelope, and you will still be left with a lot of extra. So your overall budget will actually get reduced when you design the right way in this logical sequence. You'll save money in your building construction, your first cost. And of course, you'll save over the life of the building, and you'll have a more resilient building.
That will maybe be the strongest argument of all. People love to save money. And when they look at the whole analysis, it seems like we can't avoid that.
Thanks for being on the show.
My pleasure. Thank you for having me.
Take care.
Bye-bye.